Whoa! That guy is amazing. He absolutely defies gravity.
Nobody defies gravity, not even slam dunk champions. Let me tell you what's really going on.
Uh-oh. You're not gonna get all scientific on me, are you?
Hey, this just might make you a better basketball player.
I'm all ears.
Okay, so when that power forward jumps, he pushes off the floor with lots of force. That gets him moving. And because of inertia, he keeps moving in the same direction.
Higher and higher.
Until the force of gravity pulls him back down.
Total bummer.
Not really. Without gravity, you b-ball stars would have a hard time making baskets. Because when you jumped, you just keep going, out into space.
We'd be playing moonball. So, how does gravity really work?
Well, most people think that gravity's just the pull of the Earth.
Right. It holds everything on the ground and keeps us from floating into space.
That's true, but there's more going on.
Like what?
Okay, all objects attract each other. That means the Earth's not only pulling us, but we're pulling the Earth.
Come on. I don't see the ground coming towards us, do you?
No, and there's a good reason. It has to do with mass and gravitational force. The force of attraction between any two objects.
Like the Earth and my basketball?
Or the Earth and the Moon. Any two objects.
Yeah?
Definitely. And it pulls from the exact center of each object's mass.
The center of gravity?
Exactly. So, for the Earth and other spheres, the center of gravity's right in the middle.
For my basketball, too?
Yep.
What about things that aren't spheres?
Everything's a bit different. You can find the center of gravity of a pencil by balancing it on your finger. The place where it balances is the spot.
Okay. And the bigger objects pull harder?
Well, it's hard to believe, but any two objects attract each other with equal gravitational force.
You're kidding. And how about a basketball and the Earth?
Strange, but true. They're attracted with the same force.
That's wild.
But they react differently to the force. Because they have different mass, the Earth is gigantic compared to a basketball.
So, mass is the key.
Yep. Imagine if I tried pulling an elephant. It's so heavy that it's got a lot of inertia, so my pull isn't strong enough to start it moving. But if I pulled this puppy with the same force, it'd come right to me.
Right. It's got less mass and inertia, so it's easier to move.
Well, it's kind of the same with gravitational force. Big, heavy objects barely feel the attraction, but objects with less mass are pulled towards the bigger ones.
You mean basketballs, people, puppies, and other things are pulled towards the Earth because they're so much smaller than the Earth?
Yep, that's what gravity's all about. In fact, the moon's small enough to react to the pull of the Earth's gravity too. But since it's pretty massive, it stays in space instead of being pulled to the ground. If it was the size of a basketball...
It would be pulled straight to Earth. Wow! I think I'm getting it. Gravity's the pull that keeps objects on Earth from floating into space. But it depends on gravitational force and mass. Gravitational force is the physical force that attracts two objects towards each other. It pulls from each object's center of gravity, the exact center of its mass. When two objects attract, they pull with the same gravitational force. Objects with less mass feel the gravitational force more, so they're pulled towards larger objects.
RJ, you're a real science whiz.
Yeah, well, I'm definitely attracting some new ideas into my head.
2 points.
For me and gravity.
Newton's first law. An object at rest remains at rest. An object in motion remains in motion at a constant speed and in a straight line unless acted upon by an unbalanced force.
Hey, can you give me a hand?
Nah,
Oh, RJ, this sofa's heavy. Can you help me move it?
I'm reading something. Can't we do it later?
Man, talk about inertia.
Inertia? What do you mean? I'm just chilling.
More like frozen in place. A perfect example, since inertia has to do with how things move. Or don't. It's Isaac Newton's first law of motion. The first part says that because of inertia, objects in motion will keep moving at the same speed in the same direction.
Forever?
Yep. Unless some force changes their motion.
Come on. How can something keep moving forever?
Well, think about Mia on her scooter. Once she starts rolling, she just keeps on going.
Yeah, until she runs into some gravel or something.
That's because gravel causes friction. It makes her slow down and stop.
Yeah, but she would have stopped eventually.
Not if there wasn't any friction or another force to stop her. That's the most important part of Newton's law. If Mia was zipping along in outer space where there's no friction, once she started moving, she wouldn't need another force or push to keep her moving. She'd just keep going at the same velocity forever.
Velocity? Isn't that like speed?
Well, speed and direction.
Wow. Can you imagine Mia going straight out into space?
Now that would be a trip. Speaking of trips, inertia is what makes you slide sideways when you're riding in a car that makes a sharp turn.
Really?
Oh yeah, when you're driving along, even though you don't feel it, your body's moving as fast and in the same direction as the car. If the car turns fast, your body keeps moving in the direction you were going before the turn. So if you're turning left, you'll slide to the right. See?
That's wild. I think I'm getting it. But what about the sofa? You said it has inertia, but how? It's standing still.
Yeah, and so's the scooter after it stops. Lucky for us, Newton discovered that the same rules work for all objects. So part 2 of Newton's first law says that because of inertia, objects at rest will stay at rest unless a force makes them move.
What kind of force?
Well, Mia can push off with her foot to get enough force to start moving again.
So how come you couldn't make the sofa move?
Well, the heavier things are, the more inertia they have, and the harder it is to make them move.
That sofa is really heavy.
That's why I needed your help?
Yeah, I get you. So let's go over this inertia thing again. I want to be sure I've got it. Newton's first law of motion says that because of inertia, objects in motion will keep moving at the same velocity, that's speed and direction, and objects at rest will stay at rest, unless a force changes things. Friction is one kind of force. It can make a moving object slow down or stop. Heavier objects are harder to move or stop because they have more inertia.
Impressive, RJ. I think you got inertia down.
Thanks. Now, how about I get over it and help you move that heavy thing?
Well, I don't want to force you, but I'd love it.
Newton's second law. If you apply more force to an object, it accelerates at a higher rate.
Look at that ball go! I don't know how you do it.
Just a little luck and a lot of acceleration.
Acceleration? You mean speed?
Nope, acceleration. Speed's just a measure of the distance something travels in a certain amount of time. Acceleration is a change in velocity, both speed and direction.
Oh, I guess that is different.
Definitely. Every time that ball gets knocked by a flipper, takes a sharp turn, or hits a bumper, it either speeds up, slows down, or changes direction. That's acceleration.
Wait, it's accelerating even when it slows down?
Even when the speed is decreasing, it's still acceleration. But you can call it deceleration instead of acceleration.
Whew, that's a lot of speeding up and slowing down. But what about before all that, when the ball's just sitting still?
Well, when an object is at rest, that's partly inertia at work. Inertia is the property of matter which states that an object at rest or moving in a straight line stays that way.
So, does that mean inertia slows things down?
Not at all. Inertia is what keeps things steady, whether they're moving or not. It's the constant speed of an object. What you're thinking of is friction.
What's the difference?
A lot. Friction is a force that works against a moving object, like when you ride your skateboard over gravel on the road, or when the pinball is slowing down as it rubs against the wood on the flat parts. Those are both examples of friction and how it slows things down.
So, if inertia keeps things steady, what gets them moving in the first place?
To get something moving, we need force. To start, the ball is sitting still, waiting to be rocketed into the game.
Waiting for force.
Yeah! The force is a push or pull that causes an object to move, stop, or change direction. When I launch it,
Bam!
I apply an unbalanced force, a force stronger than the one keeping it in place. When an unbalanced force is applied to an object, its velocity changes and acceleration occurs.
Nice! It went from sitting still to full speed ahead in a split second.
Right! When there's an abrupt change in velocity like that, that's when acceleration is at its peak.
And every time it changes direction, that's acceleration too?
You got it!
Whew! Acceleration's quite a ride. but I think you got me up to speed on what's happening here. Acceleration is a change in velocity, the speed and direction of an object. When a force is applied to an object that changes the object's direction or speed, acceleration occurs. And until that change happens, inertia's always at work, keeping an object at rest or moving in a straight line.
Sounds to me like you're all up to speed when it comes to acceleration, Sam. But now it's time to excel where it counts.
Newton's third law. Every action has an equal and opposite reaction.
Ow.
Zoe, watch out!
Ouch.
Hey, are you okay?
Yeah. Oh, hard bench. Guess I wasn't looking.
Now that's what I call action and reaction.
Action and what?
Action and reaction. It's Newton's third law of motion.
What?
You know Isaac Newton, the gravity guy? He realized that for every action, there is an equal and opposite reaction.
Like, if I run into you, you run into me at the same time?
Pretty much, but there's more to it. Okay, so when you bumped into me, you applied force or pressure against me.
Yeah, sorry about that.
According to Newton's law, my body pressed back against you with the same force.
Come on.
We both felt the same force because the forces from our bodies pressed in opposite directions.
Yeah, but if we hit with the same force, how come only I got knocked down?
Good question, champ. It's all a question of mass. How much matter is in something? First of all, who has greater mass, you or me?
Is that a trick question? You, obviously.
Well, according to Newton, when two objects with different mass collide, they'll accelerate at different rates.
Accelerate?
Change their speed and direction.
So, even though their forces are the same, one will accelerate more than the other?
You got it. The object with smaller mass will accelerate more.
Smaller? That would be me. So I fell, and you didn't.
Hey, come to think of it, the same thing happened with you and my soccer ball. You hit each other with the same force, but the soccer ball went flying.
I got it now. Because my mass was bigger, the ball accelerated more. How about when a baseball bat hits a ball?
Yep, both objects hit each other with equal force in different directions. The ball goes flying because its mass is smaller. The way the bat is moving when it hits can make the ball go in different directions.
And what happens when two things that are the same mass collide? Like two pool balls?
Well, what do you think?
Well, they hit each other with the same force, and the forces press in different directions, so they have the same acceleration?
Yeah.
Wow, this action and reaction thing is a little complicated, but I think I've got it. Newton's third law says that for every action, there's an equal and opposite reaction. That means that when two things collide, they press with the same force in opposite directions. That's why you and I both felt it when we bumped into each other. And when the objects have different mass, like we do, they'll also have different acceleration. The object with smaller mass, in this case me, will speed up or accelerate more.
And she scores. Now that's what I call a smart reaction.
What can I say? I'm just a genius in full force.
So you made it to the end again. You are really persistent. Here's your exit task. To receive your very own bouncy ball, apply each of Newton's laws to the ball. That's it. Explain how each of Newton's laws could apply to the bouncy ball, and your teacher will let you choose one from the bag. Good luck, and have a fantastic rest of your day.